All right, so we're going to start with the first talk by Tom Baird, and he's going to talk about epolynomials of character varieties for real curves.
All right, yeah, well, thanks for the invitation. It's great to meet you virtually. I'd love to visit Mexico City one day if that travel ever becomes possible, but it's great to be able to do this from my own office without any jet lag. Okay, so the topic is epolynomials of character varieties associated to a real curve, and it fits with the theme, I guess, of this conference, and that has to do with spaces of homomorphisms. This is all done with a joint work with Michael Wong and posted on the archive last year. Not published yet, but things move. Oh no, things move slower in the world of COVID. Okay, so here's a quick overview. Now I'm recycling a talk that was 2 hours long with two parts, so I'm not going to get to all of this stuff. But what I will do is I'll introduce the character variety in question. And then I'll explain what an epolynomial is and how it's related to Mixedhot structures. Then I'll explain a theorem of Katz's that allows you, in some cases, to calculate this epolynomial by counting points of your scheme over finite fields. Okay. And then I'll explain how one goes about actually counting points in representation varieties or character varieties over finite fields. And this ties in with the representation theory of the finite general linear group. So I'll have to explain a little bit of that subject, which is very classical and attractive. And then assuming I have time, and I hope I will present our main theorem, which is a generating function for the epolynomials of this class of character varieties I'm going to introduce at the beginning. Okay, and then I probably won't have much time after that, but if I do, I can talk a little bit about open questions and explain how these character varieties tie in with moduli spaces of Higgs bundles and other things. Okay, so just establish some notation. Sigma is going to be a genus G surface, and I'll put two little, what do you call these things? Marks there to indicate that it's a genus G surface with two punctures. Okay. C is going to be a primitive 2nth root of unity in a field K. K is going to either be the complex numbers or a finite field, typically. And so given that data, we consider the twisted representation variety, Rn of K. And this is as a set, it's a set of homomorphisms from the fundamental group of this punctured surface, two manifold, to the general linear group of rank n over this field K. And you require that say positively oriented loops around each of the punctures are sent to the scalar matrix C times identity n. Okay, so this is the scalar matrix corresponding to this 2nth root of unity. Now it's more conventional when one discusses this variety to have just a single puncture and to use an nth root of unity. But if you take two punctures and use two nth roots of unity, you get something which is isomorphic to if you have one puncture and an nth root of unity. Okay, and it's convenient for my purposes to have two punctures. Okay, so this is the representation variety. And then when K is the complex numbers, I want to consider also the twisted character variety, which is just the quotient of this representation variety under the action of GLN, which acts just by conjugating the target here. Okay, so this, because I've chosen a primitive 2nth root of unity, this character variety is non-singular. It's a complex non-singular affine variety. This is both the sort of set of orbits in the set theoretic sense. It's also a GIT orbit, GIT quotient. So it's an affine variety. And it comes equipped with a symplectic structure, which is a holomorphic symplectic structure. So not a Kähler structure, but a holomorphic one. So that will be sort of one of our objects of study. And in fact, this twisted character variety admits a complete hyperkähler metric by work of Hitchin. And this complex symplectic structure is some sort of shadow of that hyperkähler metric. Okay, it's sort of half of the data defining this hyperkähler metric is captured by the complex structure and the holomorphic symplectic form. Okay, so the existence of this hyperkähler metric is part of the source of interest in this variety, but I won't really talk about it in this. If you give me 2 hours, I would have talked about it, but I won't really talk about it. Okay. But it's nice to know it's there. Okay, so now I want to consider the same setup, but we endow our punctured surface with an orientation reversing involution, which interchanges the two punctures. Okay, and you want to think about this as, you know, this is like sigma is like a real projective curve, and tau is the Galois or the complex conjugation action on the set of complex points. Okay, but for this talk, you don't have to think of that. You could just think of a two-manifold with an orientation reversing automorphism. Okay, so given this orientation reversing involution, we can associate a couple of groups. Pi1 sigma double prime tau, this is the orbifold fundamental group, and it's defined simply by taking the homotopy quotient of this space with the involution in the Borel construction, say, and taking the fundamental group of that. Okay, so this the ordinary fundamental group will sit in here as an index 2 subgroup. Now that's a little bit fancy. In two cases, it boils down to something very simple. So if the involution has no fixed points, then the quotient space will just be a manifold, and the orbifold fundamental group is simply the fundamental group of the orbit space of this quotient here. If, on the other hand, there are fixed points, then you can choose one of those fixed points as the base point for your fundamental group, and this involution then will act as an automorphism of the fundamental group. And you can form the semi-direct product of the fundamental group of sigma double prime with this cyclic group of order 2. Okay. So that's what it boils down into in these two cases. Okay, I also want to consider an extension of the general linear group. So we'll take the semi-direct product of the general linear group with a cyclic group of order 2 via the automorphism theta here, which is a Cartan automorphism of the group, sends a matrix A to its transpose inverse or inverse transpose. Okay, and this is a group automorphism of order 2, and so you can form this semi-direct product. Okay. So the representation variety I want to consider, Rn tau of k, is as a set, it's the set of homomorphisms from this orbifold fundamental group to this sort of extended GLN, which when I restrict to these index 2 subgroups gives me a representation, a twisted representation as I presented before. Okay, so it's a homomorphism then from pi1 to GLN that sends the loops around the punctures to this, this element of the center. Okay. So I want extensions of that homomorphism to these extended groups. Okay, so the diagram here commutes. Okay, so this is the class of homomorphisms. And then in the case when k is the complex numbers, I want to consider also this character variety, which is just the orbit space or the GIT quotient of the representation variety by the conjugation action of GLN on here. On this larger group in this case. Okay, so this quotient is a complex variety. And there's a natural forgetful map. If you take one of these homomorphisms, you just forget this extension and pass to phi. And that determines an embedding of this character variety into the original character variety. And it embeds as a complex Lagrangian submanifold. Okay, so it's a complex subvariety, and it's a Lagrangian submanifold with respect to this holomorphic symplectic structure. And this is called an ABA brane in the language of Kapustin and Clayton. Okay, but I'm not really going to talk much about that. Okay, so there are essentially two cases. There's the case where there are fixed points. And in that case, you can also regard this Mn tau, this Lagrangian submanifold, as the fixed point set of an anti-symplectic involution on the original variety. Okay, so there's an automorphism of this coming from the involution. There's an automorphism of this coming from this Cartan involution. And combining those, you get an automorphism of the character variety. And this is just the fixed points for that involution of the character variety. If the Riemann surface doesn't have fixed point sets, it's a little more complicated. You'll get some path components that correspond to what are called quaternionic representations. But I'm not really going to talk so much about that. So this case was considered in a paper by Letelier and Rodriguez-Villegas, written independent of our work, and it's a very nice complement to what we do, because we do the case where you have fixed points, and they do the case where you don't have fixed points. Okay. So I'm always going to think about the case with fixed points. Okay. All right. So the topology and geometry of these things is quite intricate and very interesting. Let's consider what happens when n is 1, where everything simplifies and you can write things down pretty explicitly. Okay, so these are just homomorphisms into rank 1 matrices. So in that case, you just get an abelian group, which is C star. And so the original character variety, the twisted character variety, is a torso for an abelian group. Okay, so the idea is the abelian group here is just homomorphisms from the fundamental group of a genus G surface into C star. Okay, well, you're factoring through the abelianization, so really you're looking at homomorphisms from the first homology group to C star. The first fundamental group is the first homology group is just z to the 2g, and so you just get one copy of C star for each generator of the homology. Okay, and so you get this nice picture, a very simple description of the modular space. Okay, so this Lagrangian submanifold that I'm interested in will be half-dimensional, and it will be isomorphic to C star to power g rather than 2g. And then there'll be a number of connected components. The number of connected components depends on the number of connected components of the fixed point set of the involution on the original Riemann surface. Okay, so if you have R many, so if you have a 2-manifold and you have an orientation reversing involution, the fixed point set will be a 1-dimensional compact manifold, so it has to be a unit of circles, and it's just a matter of counting how many of those there are. Okay. And here, this will again be a torsor for a group, and this is the group. This factor is coming from the fact that if around each of these fixed point circles, you can look at the holonomy, and it turns out that holonomy has to be real, a real number. And so the holonomy will either be positive or negative, and that's where you're getting these factors of 2. Okay, so that's what the picture looks like in rank 1. Now, of course, higher rank is going to be much trickier to understand and is maybe more interesting. I'll just say that in general, you get this many components, path components, to the R-1 path components. And they're sort of labeled by what you might call Stiefel-Whitney numbers from some point of view, which are these elements in this Cartesian product, more or less corresponding to these factors here. When the rank is odd, all these components are pairwise isomorphic. When n is even, they aren't. Okay, so you'll actually have different topology on different components, different Betti numbers and that sort of thing. Okay, so this just gives you a bit of the flavor of what these things might look like. Okay, so those are the geometric objects of interest. Now I want to tell you what an e-polynomial is, and I have to talk a little bit about Mixedhot structures. Okay, so let X now just be a algebraic variety over C, maybe quasi-projective, say. I don't think that's necessary, but an algebraic variety. It doesn't have to be, it can be singular. Okay, and then you can consider the compactly supported cohomology on this variety, say singular cohomology on this variety. For each degree, that cohomology will admit a natural bifiltration called the Mixedhot structure. Okay, so this is a filtration by the weight filtration and the Hodge filtration. And it's natural because it's well behaved with respect to morphisms. So if you have a morphism of two algebraic varieties, the induced map on cohomology will respect these bifiltration. And it's well behaved with respect to array spectral sequences and that sort of thing. And I got to tell you, I came to the subject really from topology, and I was kind of amazed that this exists. It's quite incredible that you have this bifiltration that's natural with respect to all these nice morphisms and spectral sequences. It has a lot of theoretical consequences. It makes calculations a lot easier if you can work with if you can actually identify the structure. So it's really a nice structure to have. Even if you're only interested in like Betti numbers and that sort of thing, it's really nice to know that these bifiltrations exist. Okay, so given all this data, you can encode the dimensions of the various associated graded pieces of this bifiltration in what's called the mixed Hodge polynomial. So this will be a 3-variable polynomial with variables x, y, and t. T is just recording the cohomological degree of the compactly supported cohomology. You can do this with ordinary cohomology too, but for our purposes, compactly supported is more convenient. And then X and Y keep track of the bi degree and the associated graded for this Hodge filtration and the wave filtration. Okay, so some quick facts about these mixed Hodge polynomials. If X is a non-singular variety, then the coefficients will vanish whenever I plus j is greater than k. And if X is projective, then they vanish when I plus j is less than k. Okay. So if you're in a situation where X is a non-singular and projective complex variety, then your 3-variable polynomial really becomes a 2-variable polynomial, because the only contributions are coming from when I plus j is equal to k. In that case, you call it a pure Hodge structure. And this recovers the usual Hodge numbers you would have seen in Kähler geometry on compact Kähler manifolds. Okay, but if you're in a non-singular situation or you're on a non-projective thing, then you have this more general situation. Okay, and there's no eye contact happening here, so I don't know if anyone has questions. It's very awkward always, but if someone has questions, you can just pipe out. Okay, so this is really interesting. Okay, but it's also pretty hard to calculate. well, for the representation varieties I'm talking about, it's tricky to calculate. Oops. Okay, so calculating this directly is hard, but you can specialize in a few different directions and get other objects that might be easier to deal with. Okay, so for example, if I take this mixed Hodge polynomial and I set variables x and y equal to 1, then I'm left with a one variable polynomial. Effectively, all you're doing is you're forgetting about this Hodge filtration and the wave filtration, and you're just remembering the cohomological degree. And so what you get is just the Poincare polynomial, which records the Betti numbers of the compactly supported cohomology. Another way to specialize, it gives you the E polynomial. So here we leave x and y, and we set t, the cohomological degree variable, to -1. Okay, so this is a two-variable polynomial. E here stands for Euler characteristic, because if you take the Poincare polynomial and set t equal to -1, you just get the Euler characteristic that way. So you can think of the E polynomial as a refinement of the usual Euler characteristic. And just like the Euler characteristic is usually easier to calculate than the full Poincare polynomial, the E polynomial is often easier to calculate than the mixed Hodge polynomial. Okay, so it's really sort of transparent how it works with fiber bundles and that sort of thing, whereas the mixed Hodge polynomial is going to be trickier. Okay, so one amazing fact about the E polynomial is this Katz's theorem, also independently proven and earlier proven by Ito. So maybe I should call it Ito's theorem. So suppose we have a separated finite scheme X defined over Z. And suppose further that we have a polynomial f of W with integer coefficients, such that whenever I evaluate this polynomial at a prime power, the number I get agrees with the number of points in that scheme defined over the corresponding finite field. Okay, so I have a scheme defined over Z. I can consider points for that scheme over a finite field. That'll give me some number, and that should agree with the evaluation of this polynomial. It doesn't have to be for every prime power, but it should be for characteristics sufficiently large. Okay, for all but finitely many characteristics, say, this should be true.
Tom, there's a question in chat which says you might mean finite type scheme. I think that's
finite type scheme. Yes, I think so. Did I write finite type here? Oh, finite type scheme. Yes, pardon me. That's what I mean. Okay, thank you. And another chat. Perfect. Okay. And so with these hypotheses, then the E polynomial of the complex variety associated to this scheme is obtained by taking that same polynomial that was giving you the point counts and just replacing the variable by x times y. Okay, so you get this, it's reminiscent of the Weil conjectures. You get this relationship between counting points over finite fields and the E polynomial of x over C. Okay, and in fact, if this was a non-singular projective scheme, then the E polynomial captures all the information of the mixed Hodge polynomial. And so you can actually reconstruct the whole mixed Hodge polynomial just from the E polynomial in that circumstance. But in general, you only get the E polynomial through this procedure. You don't get the full mixed Hodge polynomial. Okay, so let me give you a couple quick examples to see this theorem in action. So for affine space, if you consider n-dimensional affine space over a finite field FQ, then as a set, this is just a Cartesian product of FQ with itself n times. So the number of points is Q to the n. Sure enough, that's a polynomial in Q. And so this theorem is telling you then that the e-polynomial of affine space over the complex numbers is just x times y to the power n. Okay. You can do the same with projective space. So again, if you consider an n-dimensional projective space over a finite field, the number of points is given by a polynomial. You're just essentially just adding up, you partition into affine spaces and add up the number of points in each. And then using this result, then that tells you what the e-polynomial of projective space is. You just replace the q with x times y. Okay, and indeed in these cases, the full mixed Hodge polynomial is not hard to calculate. You get these expressions. And so you're just essentially, instead of taking x times y, you get x times y times t squared. Okay. All right. Now I should maybe say, I'm pulling a bit of a fast one. The actual version of the theorem we need is a little bit more general. So our scheme, instead of being defined over Z, will be defined over Z adjoin some roots of unity in order for the scheme to make sense for our application. But this captures the character of the idea. So you're really just counting points over finite fields. And that's telling you what the e-polynomial is. I should probably keep an eye on the clock. My phone is going to die. 1 second. All right. Okay, so Hausel and Rodriguez, Tomás Hausel and Fernando Rodriguez Villegas wrote a really interesting paper in 2005, 2008, something like that, where they counted the points for the original representation variety over finite fields, and they found that it is in fact a polynomial function. And so Katz's theorem, which is an appendix in that paper, allows them to determine the e-polynomial of the representation variety just by plugging x, y into this polynomial function. And then since the conjugation action of GLN on here is free, well, the center acts trivially, but the projective general linear action is free, then e-polynomials like the Euler characteristic is very well behaved. And so all you have to do to get the e-polynomial of the character variety is you take the e-polynomial of the representation variety and divide by the e-polynomial of the group. Okay, so this gives you a formula for the e-polynomial of the character variety. Okay, so when I first heard this result, I thought it was really amazing. I think Thomas spoke about this in Toronto when I was a graduate student, and it kind of really captured my imagination. Anyway, I really wanted to do something similar, and that's kind of how this project came about. So what we did is we kind of emulated their approach to count points in these representation varieties associated to the real curve, the Riemann surface with involution. And we again produced showed that it was a polynomial function. And then we deduce in a similar fashion the e-polynomial of the character variety. Okay, so minor modification here. We have to divide by the e-polynomial of GLN because the center doesn't act trivially anymore. But it's essentially the same thing. Okay, once you have a formula here, you can get the e-polynomial. All right, cool. So now the game becomes counting points in these character varieties over finite fields. How to do it? Okay, so I'll tell you how it works for the usual twisted character variety first. So remember, sigma is this genus G surface with two punctures. And so this is a presentation. So you get the usual product of commutators, G many times. So these are the G handles. And then you get two more generators for each of the punctures. And this is the relation you impose to get the fundamental group. Okay. So given that presentation, we get a presentation for the representation variety. You have two G tuples of matrices in equal C squared times the identity, because each of these are required to go to C times the identity. So you just get C squared at the identity. And this is now an nth, primitive nth root of unity rather than a 2nth root of unity because I've squared it. Okay, so we want to count solutions to this equation over a finite field. Okay, the way you do it, and I think this will come up in Enrique Torres's talk later, or this function or something related to it anyway, just looking at his abstract. So what we do is we define, first of all, we define a class function. So this is just a function on the finite group here, which is constant along conjugacy classes. We define it as just as a counting function. So the evaluation of C on a matrix A just counts how many ordered pairs, X and Y, there are. Oh, there should be a 2 there. So ordered pairs of matrices whose commutator is equal to A. Okay. So this function actually takes values in non-negative integers, but I want to sort of think of it as a complex value function, but it's an integer value. Okay, so this is, so if I want to solve this, to evaluate this thing when G equals 1, all I do is I take this function and I evaluate it at this element here. For the general G case, what I do is you take what's called a convolution product. Okay, so you take this function C, this class function on your finite group, and you take the convolution product of that function with itself G many times, and then evaluate the resulting function at this nth root of unity. So the convolution product, if you haven't seen this before, is defined in the following way. So if I have two functions defined, complex valued functions on my finite group, then the convolution product is obtained by taking a sum over elements of the group and evaluating a phi at B and psi at B inverse A and multiplying together. So this is like the convolution product you can see in functional analysis, but this makes sense for class functions on a finite group. Okay, so that's our formula, and it sort of boils down to some convolution product of a function that, well, it's maybe kind of complicated, but it's not too hard to write it down. Okay, so what happens in this new situation? Well, you get, again, you can express it in terms of convolution products of some basic functions. Okay, so the presentation of this orbifold fundamental group was determined by Hausmann using Meyer-Vietoris and stuff. I won't actually give it to you. I won't have to give you the presentation, but I'll show you the consequence. So we define two class functions now on GLN, f and n. So f is a function, so it's given by the following formula. So if I evaluate f at a matrix A, then I'm just counting matrices B, which are symmetric and satisfy this identity. So A, B, A transpose equals B. Okay, so the way you might interpret this is, given a matrix A, I'm looking for, so B determines a symmetric bilinear, non-degenerate symmetric bilinear form because it's a symmetric matrix. And I'm looking for symmetric bilinear forms for which A is orthogonal. So they're fixed under the natural action of A on symmetric bilinear forms. Okay, so you fix an invertible matrix, and you're counting how many symmetric bilinear, non-degenerate symmetric bilinear forms A is orthogonal with respect to which. So it's sort of a natural question, but I don't believe, as far as I know, this function hasn't been considered in the literature before our paper. But maybe I just haven't found the reference. I don't know. And then the other function, n of A, which has been considered before. This is sort of calculating square roots of A. So you're looking for matrices B and GLN such that B times B inverse transpose is equal to A. Okay. So these are both class functions that take values in non-negative integers. Now, if the fixed point set of this involution has R many path components, then I claim that the point count of this variety over the finite field can be expressed as follows. So if the orbit space is orientable, then you take R many copies of F and S over 2 many copies of C, where S is given by this equation. Take the convolution product, then you evaluate it at C at this point, okay, at this matrix. Okay, and if it's not, then you do something similar, where you take a convolution of copies of F and copies of N, and then you evaluate it at the central matrix that defines our character variety. Okay, now a representation theorist named Roderick Gao introduced this function n in a paper of his in representation theory, and he proved that if you take the convolution product of n with itself, you get C, this function that's related to counting commutators. Okay, so that means that I can replace C here by n squared, and you actually get the same formula in both cases. Okay, so from the presentation, this is what you get, but in fact, through a theorem, the formula actually doesn't depend on whether the orbit space is orientable or not. It only depends on the genus and the number of path components. Okay, and so that means that the point count and consequently the E-polynomial is independent of the orientability of this orbit space, which is interesting because the topology does depend on the orientability. Okay, so if you have, you can show the Betti numbers are not in agreement, but somehow this special Euler characteristic, this E-polynomial, is independent. Okay. All right. So very good. Now, how do we evaluate convolution products of functions? It's all nice to have this formula, but can I actually calculate anything? Well, if you've seen convolution products at all before, you may have seen them in the context of Fourier transforms. Okay, so it's a beautiful fact that if I take, say, complex valued functions on the real line, and I take the Fourier transform of their convolution product, then I end up with the ordinary pointwise product of the Fourier transforms. Okay, so the Fourier transform intertwines convolution and ordinary products. Okay, and this turns out to be true on finite groups as well. So if I have a class function on a finite group, if you remember character theory, we can always express that. So the irreducible characters of the finite group form an orthonormal basis for the space of class functions. Okay, so any class function can be uniquely expressed as a linear combination of irreducible characters. And it's orthogonal with respect to this inner product. And the theorem says that if I take the convolution product of two class functions and I look at the multiplicity of a certain irreducible character in that convolution product, then that's essentially just the product of the multiplicities of each of those constituent functions times a correction factor, which is easy to understand. Okay, so this is essentially just that rule from Fourier analysis, that if I take the Fourier transform of the convolution product, I just get the product of the functions up to some correction factor. Okay. So what this is telling you then is that in order to understand these convolved functions, it's really enough to express f and n in terms of this irreducible character basis, and then convolution products become very easy. You're just doing ordinary products. N and F in terms of the irreducible character basis. So we want to calculate sort of multiplicity of irreducible characters in these. So both N and F turn out to be characters of representation, so they're the trace of some representation of the group. And we want to find the multiplicity of these irreducible characters. Okay, so thankfully, Roderick Gao did the job for us for the function N. This is the sort of counting some square roots, essentially. And he proved this remarkable fact that N is actually just the sum of all of the irreducible characters of the finite general linear group, each with multiplicity 1. Okay, and this is a consequence of some interpretation of these coefficients as a Frobenius-Schur indicator, if you have ever heard that term before. But it's a nice result, and it's a very curious result. Okay. Okay, and then when Enrique gives his talk later, C, I'm anticipating that the function C will come up, and then that's just obtained by taking for GLNFQ, not for general finite groups, for GLNFQ, that can be obtained by taking the convolution product of bandwidth itself. Okay, so you'll see that formula I showed before. I'll come up again. Okay, so that's half of our work done. And then we're left with this function f, which is counting how many non-degenerate symmetric bilinear forms are left invariant under our matrix A. And so that has some expression as a linear combination of these irreducible characters. And I'm just going to call A chi those multiplicities. Okay, so as I said, this is actually the character of a representation. So these will be non-negative integers that appear here. Okay, and we want to try and calculate. Okay, so the calculation is sort of long and complicated, but it's very easy to explain with basic strategy because it's fairly simple-minded. Okay, so the first thing is to actually come up with an explicit formula for f. To do that, we use this paper by Milner, which classifies orthogonal transformations over perfect fields. It's a very nice paper, you get a formula fairly quickly. It's a little bit complicated, but inside a week we had written down a formula. And so then you want to calculate the multiplicities of these representations of these characters in F. Okay, and you can think of that in terms of the inner product. You just take the inner product of F with the irreducible character, and that gives the multiplicity. Doing that for a fixed N is very complicated, okay, because the representation theory of these finite general linear groups, it involves all these green polynomials and things. It's combinatorially very tricky. But if you consider a limit when the Q goes to infinity, so Q is this prime power, the order of the finite field. If you take the limit as Q goes to infinity, then a lot of the complication disappears. Okay, and you have all these polynomials cropping up, and you can essentially ignore everything except the leading order terms, and you can actually get formulas. Okay, so you have to calculate the multiplicity in the limit when Q goes to infinity. And then you actually have to show that this is a valid process. Okay, so that you're going to get some value here, and it has to be remain valid for sufficiently large characteristic. Okay. So what I'm doing here is a little bit fishy, and you have to do some work to actually justify what's happening. Okay, but that's essentially how the argument goes. All right, so I think I have 14 minutes. Is that about right? Sound correct?
The talk was supposed to be 45 minutes.
45 minutes. Oh,
yeah.
Oh shoot. Okay, so, I didn't know that. Okay, that's too bad.
But maybe we can do like, I don't know, 4 more minutes, like 2 till 10.
Sure. Okay. So I thought it was an hour-long talk, but so I won't be able to tell you about the representation theory of the finite general linear groups, even though it's a very beautiful topic. But it's yeah. So it has to do with partitions, like Young diagrams, and is tied in with Frobenius orbits of the algebraic closure of the corresponding field. Okay, and it's a nice, very nice dictionary that gets you to the classification of the irreducible representations. And in terms of that classification, you can get nice formulas for the multiplicity of these characters, which I don't really have time to explain. But what initially appears like it would be very complicated, and it boils down to actually something fairly simple. And in fact, the governing formulas are certain identities involving Schur functions, like the one here. So it boils down to certain coefficients that appear in Schur function identities, where you're taking the sum over all Schur functions, and then you're taking a sum over Schur functions for kind of trivial partitions, and quotients of these things. Okay. Anyway, this was an amazing discovery when we found it. It was a delight, but I don't think I can quite persuade you of that in the time I have left. And then we get these this really nice formulas for the e-polynomial. So here's the formula of Hausel and Rodriguez-Villegas. So they take the e-polynomials of these character varieties using q instead of x times y, just for simplicity. And you take the sum over all of the e-polynomials for all ranks. So starting with rank 1 up to rank infinity, and then you have a variable t to the n, which keeps track of the rank, and then you have some little correction factors hanging around. Okay, so that's one side where the e-polynomials are. And on the other side, you have the logarithm, or the plothistic logarithm, of a sum over partitions, over Young diagrams. Okay, this is a purely combinatorial thing on this side, and this is a geometric thing on this side. Okay, so on the right hand of this formula, we have what's called the plothistic logarithm, which is the inverse of the plothistic exponential, which is given by this formula here. And these h lambdas are certain what called a hook length polynomial, which is a polynomial you can associate to any Young diagram by sort of, this formula. But this is a well understood thing. It comes up in representation theory of the symmetric group and so on like that, combinatorial representation theory. Okay, so this is an amazing formula, and it's intrigued a lot of people, and there are interpretations in terms of mathematical physics and Gopa-Kumar-Vafa invariance, and it hasn't been proven in full generality yet, though it has in some cases. And what we do is an analog of their result. Okay, so we again get a generating function for the e-polynomials. Resembles theirs a great deal, although there's some sort of taking square roots of certain things over here. And on this side, well, we get a more complicated expression. So we have an infinite product, and these coefficients I mentioned briefly on the other side crop up, but you have this really nice formula over here. Okay. What kind of interpretation does this have in mathematical physics? I don't know, but I'd love to find out. Anyway, that's all I have time for, so thanks for listening.
Thank you.
Thank you.
I'll restore your faces now.
So
any questions? Sorry about going over time.
No. I should have reminded you maybe. So very nice talk, Tom. Are there any questions for Tom?
Yes, the notes are being posted for the entire thing, right? Not just the part you got to, but the remaining slides will all be posted. Is that right?
I'm happy to show them.
Yeah, maybe we can do that. So Tom, you're not interested in the case of genus 1?
Oh yeah, the case of genus 1 is covered. In fact, the case of genus 0 also is covered. So the formula works for genus 0 as well.
Oh, okay.
So genus 0 and genus 1 are excellent test cases to make sure the formula actually makes sense. But you can sort of work those out directly as well.
I see. There's a question from Lisa in the chat.
Right.
Can make the question, if you restricted to the case where you have two boundary components and the holonomy around each of them is in the same class. You had this psi and
Right.
it was the same holonomy for both of those. Can you study the case where you fix two different values, still two boundary components, and you make that restriction?
Only the product of those two values don't matter.
Yeah.
Yes. So the reason I have two boundary components is so that my automorphism on the Riemann surface will interchange the two. And if I have different holonomies, then you'll no longer have an automorphism.
Okay.
Oh, right.
of the character variety.
Okay, I understand.
Right.
Thanks.
It certainly would be interesting to take, other conjugacy classes, the same on each, but you'd get some kind of parabolic moduli space in that case.
Mhm.
Yeah.
Thanks.
Okay, so are there any other questions? Well, if not, let's thank Tom again.
And thanks again to the organizers for having me.
So we're gonna have a 6-minute break. We resume at
Sorry for going over time.
no worries.